Hello, my name is Enya McHale, and today's presentation for EME 497 Geothermal Energy Engineering will cover drilling. The first thing to understand about this is what is drilling. Drilling is the action of making a hole in something by boring it with the drill. Geothermal energy, it is also used to sample the rock and the soil that is in the subsurface. It allows for determination of several factors. These include thermal conductivity, porosity, permeability, the rock type, physical characteristics of the subsurface, the temperature gradient within the subsurface, and then any other factors that will influence the evaluation of the resource. Drilling has been used for the last 100 years in the production of energy, and it is one of the most important developments in the energy industry. It's used to access traditional fossil fuels such as oil and gas, and in terms of geothermal energy, it's used to access the geothermal fluids below the surface and access a constant supply of heat at a controlled rate. When going through a project, it is one of the most expensive undertakings and therefore requires a lot of planning to ensure that the location where the drilling is occurring is suitable for the process. Like any highly specialized project, there is specific equipment that is needed to drill. This includes drill rigs, drill bits, drilling fluid, casings and grouting, packers, and Christmas trees. For any drilling process, a crucial piece of equipment is the drill rig. It is a machine that creates holes in the Earth's subsurface. For different jobs, there are different types of drill rigs that are used. For oil and gas, there are ones that are on the water and ones on land. For geothermal energy, it's mainly ones that are on land, and they can either be stationary or mobile. The rig that is shown in the picture on the slide is a stationary rig. The next crucial part of equipment to discuss is the drill bit. The drill bit is the tool that creates the cylindrical hole. For different jobs, there are different drill bits that are needed. This picture shows 3 different drill bits: a polycrystalline diamond compact bit, a natural diamond bit, and an impregnated bit. Depending on the subsurface, different bits will be needed, and depending on the scale of the job, different bits will be needed. The drill bit is connected to the drill string, and that is what controls the drilling. While there are a multitude of different drill bits, there are also a multitude of different drilling techniques that are used for different projects. The 2 types we will discuss in this presentation are percussion drilling and rotary drilling. The first one we'll discuss is percussion drilling. Percussion drilling is best used for small diameter short holes. In this process, the drill bit and the drill string are repeatedly raised and lowered by the rig to impact the rock below in the subsurface. Pneumatically driven percussion uses a mechanical device attached to the bit that repeatedly jackhammers the bit into the rock. The second drilling technique that we will discuss is called rotary drilling. Rotary drilling is best for deeper, larger holes. In rotary drilling, the rock in the subsurface is shattered by applying pressure to the rock with a rolling cutter. For a softer rock in the subsurface, roller bits are the better type to use. If the rock is harder, then a diamond bit is the preferred piece. Another important safety feature is the drilling fluid. The drilling fluid is a circling fluid that is used to remove cuttings and any other debris that may occur from the well. The drilling fluid is injected down the drill string as the drill string drills and returns the fluid back to the surface via an annulus in the pipe. The fluid is called drilling mud also. This is a result of the fact it is made up of a mix of water and clay normally. An important thing to note about drilling fluid, especially in terms of geothermal energy, is that temperatures of about 200 degrees Celsius is about the limit for standard drilling fluid. After that, it starts to become compromised. So therefore, specialist drilling fluids need to be used during production of a geothermal well. Another important factor of the drilling fluid is the fact that it performs functions that make the well economical. As mentioned before, it clears cuttings. Cuttings are important to clear as they can damage the drill string or cause blockages. They lubricate the string and the bit, which allows them to move easier and less likely to break. Another important thing it does is it stabilizes the well. If the well is not stabilized, it could collapse in on itself, which would therefore damage the drill string if it was still down there, or be a total loss of the well. This brings us on to another important part of the drilling process, which is the casing, cement, and grouting. These are important because they allow for the permanence of the hole. It's no good to drill your hole and then have it collapse in. It also protects whatever equipment might be left down in the hole, which might be some types of sensors, which is expensive, and therefore you don't want any collapses to happen. Another really important part of doing this is the environmental protection that it creates. When you drill through the subsurface, you have the chance of running into aquifers and other natural formations that you want to protect from whatever you're bringing up from down below. So the physical isolation of the well is very important. Another crucial equipment for the well is something called a packer. A packer is a safety device first and foremost. It allows for a section of the well to be sealed off that might have problematic properties that could affect the overall production and safety of the well. It is desirable to isolate these zones because they might have issues with porosity or permeability that don't make it economical to use. The packer is lowered into the well, so it must have a diameter smaller than the casings and pipes. Once it is in position, it is inflated using high-pressure fluids, which can be air or liquid, and it seals tight, therefore closing off that area. Multiple packers can be used in the same well, as with different depths there are different issues. Another great thing about a packer is it can be used to stimulate a certain part of a well. We're now going to look at another safety feature. However, this safety feature is above ground, unlike the other subsurface ones we've looked at before. This is a really crucial one, and it's known as a blowout preventer. Due to its shape, it is also known as a Christmas tree. It's really crucial to have a blowout preventer on a well due to the fact, especially geothermal wells, are kept at high temperatures and under very high pressure. In some cases, it's also possible for toxic or combustible gases to be present in the well, and therefore you want to stop any uncontrolled release of anything that might be in the well. This could be the toxic gases, any fluids that are there, or steam. The Christmas tree or blowout preventer is installed after the well is cemented, and it is really one of the most important safety features a well can have. Now that we've looked at the key safety features, we can look at the types of drilling that actually occur. Previously in the presentation we looked at more the techniques, and now this type of drilling refers more to the direction that the drill string goes to once it's in the subsurface. There are three types we will look at: vertical, horizontal, and deviated drilling. Vertical drilling used to be the most common form of drilling, and it is quite simply a direct descent into the subsurface. As previously mentioned, most wells were originally vertical wells. However, as time has gone on, we have now moved towards a more deviated and horizontal drilling style. This deviation is really important as it allows for greater access to the whole reservoir, especially as reservoirs can be huge, vast distances. This ability to access more of the reservoir is important because it reduces the number of drill pads needed, as you can drill several directions from one drill pad. An important thing to note is that having this deviated drilling and horizontal drilling does increase the costs of the project around 20%, but it is normally made up for in the fact that there's higher production of the reservoir. So in deviated drilling, as it goes down, it gains directionality, so it can have a curvature of about 15 degrees for every 30 meters. And this deviated drilling, horizontal drilling, has become the standard in geothermal energy. Another thing to note, however, is any type of deviated drilling or horizontal drilling, there are more risks involved than standard vertical drilling. And then when you add in the high temperatures that are related to geothermal drilling, there are more risks of failure with the equipment. So this needs to be taken into account when starting a geothermal drilling project. Another important process happens during the evaluation of a reservoir. It's called coring. As you can see in the picture background of this slide, that is a sample of a core that's been taken up from the subsurface. Coring is a really crucial process because it allows for evaluation of subsurface, as you can see samples of the rock. It is done by drilling smaller holes with a special bit that tends to be smaller, and it brings the rock back up in a cylindrical piece instead of in cuttings like with the traditional drill bit. When it's brought up, depth markers are added to the core piece, so engineers and scientists are able to evaluate what is going on within the reservoir. This is really important because it can aid in knowing which type of drill bit to use and any other issues that might come up in the well. Even though geothermal energy is considered a green and renewable energy source, there are still some environmental concerns that go along with it that are very similar to those of traditional fossil fuel processes that involve drilling, such as oil and natural gas, especially fracking of natural gas. So the main concern is possible contamination of the groundwater due to the fact that some of the wells might go through aquifers. Therefore, it is really important that the casing and cement jobs are done well to stop any contamination. A really big part of this that causes environmental degradation is the drilling fluid once it's being brought up. It requires a pit to be dug near the drill rig, so once the process has been finished, this pond of drill fluid does need to be rectified so that the land can be brought back to how it used to look, as people do have concerns about landscape damage and environmental damage. Different projects have different rules due to local regulations varying, so therefore this needs to be taken into consideration before a project starts, as some of the cleanup processes are very expensive. Now that we've discussed the process of drilling, we are going to look at an actual geothermal field. The geothermal field that we're going to look at is the Conda Geothermal Field in Japan. It's located 500 kilometers north of Tokyo. The field is one of the world's shallowest high-temperature geothermal regions and is located within the active Toku volcanic arch. The Toku volcanic arch is a part of the subduction zone complex that bounds Pacific Plate in the western Pacific region. The Conda geothermal field has more than 70 wells that have been drilled in the area, and most of these wells reach between a depth of 1,000 meters and 3,000 meters, or 1 kilometer to 3 kilometers. The temperature distribution as a function of depth is variable within these wells. Power has been generated in this area since 1978, and currently more than 70 megawatts of power is generated in the region each year. This is really impressive and a very important field due to this. A thing that's really important about this field is it shows that geothermal energy can be extremely successful, and it can also have its issues. So when a well was dug in the Conda geothermal field in 1994, they ran into issues that occur due to the nature of a geothermal reservoir. The first sort of issues began to appear at 3,000 meters, which is a traditional depth for issues to occur due to the fact that temperatures are reaching the range when drilling fluid starts to become compromised, as we discussed in a previous slide. So at a depth of 3,350 meters, excess CO2 was discovered in the drilling fluid. Drilling fluid is really good because it can show what's going on down the well and when it's brought in back up, and you can also treat what's going on down the well. So to combat the CO2, lime was added to the drilling fluid, which then turned the CO2 into calcium carbonate. This was a successful effort to mitigate issues within the well. As drilling continued, further issues were discovered at different depths. At 3,451 meters, the drilling fluid had deteriorated to a point that it needed to be replaced with one that had a lower density due to the temperature. It's important to make sure the drilling fluid works so you don't damage the drill string or the drill bit. However, once this issue had been mitigated, at a further depth, another issue appeared. High concentrations of H2S was discovered, which is also a health hazard and needs to be dealt with. The way to deal with this with drilling fluid is to increase the density and the viscosity of the mud, which counteracts what happened to deal with the temperature problem before. When the temperatures at the bottom of the well became elevated, it became an issue, and production was stopped at a depth of 3,729 meters, which is still very deep. Once the well had been drilled and completed, downhill surveys were conducted. It was found that the well at the bottom reached a temperature of 5 100 degrees centigrade, which at the time was the hottest measured geothermal well. As this field shows, there are many benefits of geothermal energy, but it is a very difficult process that will help our energy needs of the future. Thank you for watching this presentation on geothermal drilling. There are questions that go with this presentation on Canvas.